Hi there, we're looking at gases today. You've already read in your textbook, or a textbook looking thing. Your textbook doesn't do as stellar of a job as this textbook does, so I found this one, about the 3 assumptions of the kinetic molecular theory. About that gases are really small, they don't repel nor attract each other, and they're always moving. So those 3 things you've already covered. What I want to talk about in this video are the variables that we use to describe gases. So we're looking at things like pressure and volume and temperature and moles. Specifically, what I want to focus on first is number 1, pressure. You can see the units afterwards are kilopascals, a unit that you don't normally hear. In the United States, you usually use pounds per square inch. That's what you want to pump up your tires with for your car or your bike. But kilopascals is actually the SI unit. Remember, that's the scientific system, is kilopascals. So let's talk about what pressure really is as we talk about gases. Pressure is technically the force exerted by a gas per unit surface area of an object. Feel free to pause this at any time. So if we look at that really carefully, what that says, it's the force exerted by each gas per surface area. If you take a look at the figure down at the bottom, on the bottom left, it kind of shows that. Now, I can provide pressure onto things like pushing on a table. That's providing pressure because I'm providing a force to a set area. Gases can do the same thing, but we have to think they're really small. So the gases are zipping around this room all the time, and the gases are hitting something and then bouncing off. So for that split moment that it hits, it is providing a force against a surface. So we know that gas pressure is any time that it's hitting the walls. Now, of course, you can hit the walls faster. That'd be a harder hit. That'd be a higher pressure. Or you can hit them slower, if you're a slower moving gas particle, and then you'd have less gas. You'd have less pressure because the gas is hitting less hard. You can have a time when you've got a vacuum, and I think you've heard of vacuums before. A vacuum, technically in the science world, is when you have the container, like what you can see in the very middle here. This is a vacuum. It actually contains nothing. There is nothing in there. There's no gas, no solid, no liquid. There are no atoms at all. A vacuum is a place where you've got no gas particles, thus you have no pressure. You have no pressure because nothing's hitting the sides. This would be an example of a vacuum. Space is a vacuum. It has no gas molecules. It's just nothing, which is weird. I know some of you are thinking, but what about dark matter and things like that? Yep, I know, but right now we're just looking at gases. So dark matter could be out there. We haven't proven it yet, but we theorize that it's out there. But a vacuum is technically no gas particles. And this container has no gas particles. So nothing can hit the sides, so you can have no pressure. So when we talk about pressure, we're usually talking about atmospheric pressure. Like currently, me and you sitting in this room, we can feel pressure from us, and that's from the atmosphere. And it results from all the gas collisions that are directly above us. So if you think about the gas that's directly above me, it is hitting me, and it's providing a pressure, a direct force. But if you consider the gases that are above me, right by the ceiling, they're hitting gas molecules below it, which are hitting the gas molecules below that, blah, blah, blah. So eventually, the force of that gas molecule up at the top is pushing down on me too. It's just from a series of different hits. So atmospheric pressure is the additive of all of the gases that are directly above me. So let's think about when you go up a mountain. Here's you, going up the mountain. As you walk up the mountain, the pressure decreases, which means gases are hitting you less frequently. And the only reason that can happen is because you actually have less gas above you. As you walk up the mountain, there's only so much room between you and when space starts. And there's less gas molecules between you and when space starts. So if there's less gas molecules above you, there's less things hitting you, there's less pressure on you. So there's less pressure on the top of a mountain than there is down here in Chicago. Thinking about pressure, we've got to look at units. These are the different units for pressure. That first one, ATMs, is atmospheres. That's a frequent one. The next one is mmHg. mm is millimeters. Hg is mercury, so these are millimeters of mercury. Or torr, might have heard that before, or kilopascals, or there's bars or millibars, or like I said at the beginning, you could use pounds per square inch. That's a pressure unit we tend to use in the United States. You don't have to memorize these numbers, you just have to know how to convert them. So one thing to know is that 1 atmosphere, which is 760 millimeters of mercury, 760 torr, 1.3 kilopascals, that's where the pressure is at sea level. Now we currently aren't at sea level. We're kind of walking up a mountain. We're above sea level. So our pressure is actually less than 1 atmosphere because we are technically higher in elevation than sea level, like New Orleans. New Orleans is actually below sea level, but something on the coast would be at sea level. Okay, so let's look closer at this millimeters of mercury thing. The atmospheres thing kind of makes sense, but the millimeters of mercury, that's a little different. We can measure the pressure using barometers. Now, I'm sure you probably don't have this kind of barometer at your house, but you might have some sort of barometer at your house. All right, here I've got a beaker. As you can see in the figure there, there's a beaker-looking thing. Mine's filled with water. The picture is filled with mercury. And it's got a column, it's this big test tube here, above it. As you can see in that picture that they have a vacuum where there's a space where there's nothing. I've got that up here too. And what happens is, if you actually take mercury, and this was all mercury, the distance from where this line is all the way to where the water level is 760 millimeters. That's why it's called, at 1 atmosphere, 760 millimeters of mercury, and why we use those units. So if I had this bucket at sea level and I had mercury, it would be 760 millimeters from top to bottom. How that works is that there's pressure pushing down on us. The weight of the atmosphere, remember the atmospheric pressure is all of gas particles pushing down, they are pushing down into this beaker. And as they push down into this beaker, they're pushing on the water. And indirectly, the water is pushing upwards too. The water is pushing upwards on this column of water. Oops, I got a bubble. It's pushing upwards on the column water. At the same time, the weight of the liquid is pushing downward. So this column water doesn't move as long as the weight of the world or the atmospheric pressure doesn't move. So a push down is actually a pushing up on the column, and that's what keeps the water up where it is. Now, of course, if I took this bucket up a mountain, then the weight of the world is pushing down less. If the weight of the world is pushing down less, then it's pushing up less, and it can't hold the column as high. So this column of water, or mercury in most cases, will have to move downward. So as we work up a mountain, it's less than 760 milliliters of mercury. It's a lower pressure. If you have a barometer in a house, I am fairly certain it doesn't have any mercury in it. It's really a mechanical thing, the one in your house, if you've ever seen it. It's a dial that goes back and forth. It just has springs on it that kind of measure the weight. And when I say weight of the world, it's really the pressure, the atmospheric pressure that's pushing down. That's how a barometer works. Okay, so we got through pressure. Now we got to look at volume. Volume for a gas, we're going to have to look at liters. That's the SI system. And gases are compressible, so we can put them into tiny spaces or big spaces. So knowing how much space it is really important. We've got to look at temperature. Temperature is actually being in kelvins. I don't know if you remember, but we did calculate in kelvins before. And temperature is technically the speed of the molecules, or technically the average kinetic energy of the particles. So kinetic energy is defined as that 1/2 m, m stands for mass, times v, this is velocity, squared. So if I was a gas molecule, my kinetic energy would be my mass times how fast I am moving as a gas molecule. The speed, or the velocity, squared. Velocity and speed are technically the same thing, but in this class they're going to be close enough because we're not going to look at vectors until you get to physics. So temperature is the average kinetic energy, which is really looking at speed, because a molecule himself won't change in mass. He just has a certain set mass. So if you have a room that's really high in temperature, take a look at this chart. Here it's looking at kinetic energy along the x, number of objects or gas molecules moving at that kinetic energy on the y-axis. So at a hot temperature, that's a red line, we can see that the average kinetic energy, that's kind of like the middle of the peak, is right here. It has a high kinetic energy. They are moving fast. Look at a little colder. Take a look at room temperature. The average is right here. They are moving a little bit slower. At a lower temperature, you move slower. Take a look at the coldest, that's a blue line. They're moving even slower. As the kinetic energy decreases, we know the speed of the molecules is decreasing. So from here on out, you have to think of temperature as speed. Hotter you are, the faster you move. So the temperature scale, we're back to this Fahrenheit, Celsius, and Kelvin system. If you don't remember how the equation for it, you will start to remember now. The temperature in Kelvin, that's TK, is equal to 273, oh, this is terrible writing, I'm sorry, plus the temperature in Celsius. Normal room temperature might be something like 22 degrees Celsius. So 22 plus the 273 would get me the temperature that is in Kelvin, which is 295. I should just stop writing. You're right, I'm done. The great thing about the Kelvin system, actually, if you look at the lowest possible temperature, is 0 Kelvin. Notice it doesn't say 0 degrees Kelvin, it's just 0 Kelvin. Kind of like, okay. That's the coldest, theoretically, we can possibly get it. That's equal to negative 273 Celsius, or negative 460 Fahrenheit. That's cold. The Kelvin system is great because it doesn't have negative numbers, which is really going to be important for when we get into our gas laws here. All right, moving along with variables. We're on the last one, number of moles. Moles, we know, can stand for as N. So N is a symbol for moles. They couldn't use M because M was for meters, so they picked N, N for moles. And in the SI system, moles is moles. Taking a look at these beakers, we can see that one has 4 moles, we could say, and this one has more moles, and then they poured them together and it has lots of moles of gas. What I want to talk about with moles is Dalton's law. Dalton's law says the gas pressure depends on how many gases you have and not the type. The number of gas particles. Number of gas particles makes me think of moles. Moles is a way to measure amount of gas particles. So it depends on the amount of gas, not the type of gas. If you take a look right here, these are different, they're trying to represent gas molecules inside a container. And when gases are moving, they're clearly hitting the side. You can see I have 4 gas molecules here, and its pressure is 6 atmospheres. And this beaker, totally different kind of gas, moving around. They're a different size, that doesn't even matter. It's just the amount of the gas, not the kind of gas. This has 3 atmospheres. Fewer gases, fewer hits, means a lower pressure. So Dalton was able to do some fancy math with this. You can see all the words that he's using. At a constant volume and temperature, the total pressure exerted by a mixture of gases is equal to the sum of partial pressures of the component gases. That's just a lot of words. All those words in math form is what the equation is. So really the words are saying the exact same thing as the math. Whichever one makes more sense to you is what you should write down. Let me tell you what this actually means. So if I take my 3 atmospheres of pressure and my 6 atmospheres of pressure, we know that 6 and 3 make 9. So my P1 might be 6, my P2 would be 3. My P total is, if I pour these gases into the same container, same size container, all the gases at once, what do you think the pressure of this container is now? You might have guessed it. Yep, it's 9. The pressure, the total pressure, is just the additive of all the individual pressures. Doesn't matter what kind of gas it is, just how much of the gas you have. So that's all Dalton's pressure is trying to say, Dalton's law. If you have these individual gases, like in this one, gas A, B, and C, you can just add all their pressures together, and that'll give you your total pressure. That's why the 200, that's the gas of gas A, the pressure of gas A, and the 500, pressure of gas B, plus the 400, pressure of gas C, is going to equal, if you poured them all together in the same container, the 1100. Hope that makes sense. That's all that Dalton's trying to say. All right, we learned a lot about gases. You learned about the KMT theory, and now you know about the 4 variables, pressure, volume, temperature, and moles that we're going to be talking about throughout this chapter. Please go to the Google form and answer them as best as you can. If you don't do a good job, I forgive you. It's okay. I just want to know what you know. Good luck. I'll see you next week.